Hello, and welcome to your last lesson in Unit 6 and your last lesson of the first semester. Can you guys believe we made it? Y'all, this has been crazy, but we're here and we made it to the almost end of first semester. So our last lesson, we're going to be talking about something called qualitative analysis. And I put this here at the end of this unit because it's all about how we separate things out, and most common is going to be out of a solution. So that's how we kind of put it here at the end of this unit. So what is qualitative analysis? Qualitative analysis, pay attention to the word qualitative. We're not doing any type of numbers or measurements here, okay? So it's just identifying elements or compounds that are present within a sample. So we've got something like a mixture, whether it be homogeneous or heterogeneous, and we're trying to separate out the different components. There are kind of 5 main ways. There are probably others, but there are 5 main ways that we're going to touch on. 3 of them we're going to go into detail about. 2 of them are pretty straightforward and you should already know. Evaporation, we all know what that is, right? We're taking a liquid and we're vaporizing it. So in order to maybe filter out like salt, you can evaporate all the water off and you're going to be left with the solid salt. Pretty simple. Filtration, also very simple. If you've got some kind of mixture, like it could be a precipitate that has formed from an aqueous solution, something as simple as sand in this example. We're going to filter it. It's going to take it out based on its size, and the things that don't fit through the filter paper are going to remain. So again, super simple, something you already know. The other 3, we're going to go into a little bit more detail. We'll talk first about distillation. It's also very simple, just might be one you're a little less familiar with. And then we're going to really go into detail about selective precipitation and chromatography. So distillation, you've probably heard of it, but if not, it's a way to separate liquids. So in distilling something, we're separating one liquid from another liquid. So like we've got a solution of 2 liquids and we're going to separate one out, or maybe more than 2, but at least 2. The way that we are going to separate these liquids is by taking advantage of their different boiling points, okay? So because things boil or vaporize at different temperatures, we can get this liquid to a specific temperature where one of them starts to vaporize. And then once it vaporizes, it will actually travel through the condensing tube where it will condense back into a liquid and fall into this flask. So now what we'll have in this flask is just the one liquid. Okay, next one we're going to talk about is selective precipitation. And this really is the one that falls easily into this unit because we've been talking about solubility and we've been talking about precipitating out. And in selective precipitation, we use solubilities and precipitation to separate these things out. So ions can be separated out of solution based on their solubilities. So in the distillation, we took advantage of differing boiling points. In filtration, we take advantage of differing sizes. In evaporation, we take advantage of different boiling points. Here, we're taking advantage of different solubilities. So we're going to use a reagent that precipitates with one or a few of the ions that are present. So we've got a mixture of different ions present in solution, and we're going to add a reagent that only precipitates one of them or a few of them. So this example that's here, we've got lead chromate that formed when we had sodium chromate in solution, and we put in some, we had lead 2+ in solution. We put in some sodium chromate, and when the chromate and lead combine, they make that solid. So how do we take advantage of the solubilities? Well, we've already learned in this unit that the smaller the KSP, the less soluble something is, and the more likely or the quicker it's going to precipitate out. So let's compare silver chloride and copper 1 chloride. Copper 1 chloride is relatively soluble, 1.2 times 10 to the negative 6, while silver chloride is not particularly soluble or less soluble, 1.8 times 10 to the negative 10. So let's say in this mixture, we have silver ions and we have copper ions. we need to add a source of chlorine because it's chlorine that's going to form a precipitate with each of those ions. So maybe we add hydrochloric acid. So this would be HCl. Now, as we add it in, again, we have copper ions present and silver ions present. Because the silver chloride has the lower solubility, it's going to be silver that precipitates out first. So this solid right there is silver chloride. Because of its lower solubility, whenever the silver and chlorine come together, they're going to form solids well before the copper forms a solid with the chlorine. Okay, so when we are trying to do selective precipitation, we kind of have a procedure that we follow based on the different solubilities that we know of for common ions. And so what we've done is we've separated them into 5 major groups, and so then we try to precipitate out each group one at a time. Now, in a solution that we're trying to take these ions out of, we're typically not going to have all the ions present. There's only going to be a few ions, and typically they're only going to be 1 per group, okay? So group 1, the first thing that we're going to do is we're going to precipitate out any insoluble chlorides. So we're going to add something like hydrochloric acid, which is going to give us chlorine ions. And anything that is insoluble with chlorine, such as silver, lead 2+, and mercury, are going to precipitate out. We would remove them through light filtration, and we would have that separated. Next, we're going to do the sulfides, because sulfides are another group that are typically insoluble. And we're going to start with sulfides that are insoluble in acid. So we're going to add hydrosulfuric acid, which is going to precipitate the most insoluble sulfides. And we're going to remove those. Then what we're going to do is we're actually going to make the solution basic. And by making the solution basic, then adding more hydrosulfuric acid, it's going to precipitate out the remaining sulfides, or things that are insoluble in sulfides, those that are a little more soluble. And so by making it basic, we're going to make more of those precipitate out because we're going to decrease their solubility. So then we're going to take those precipitates out. Then we're going to go for our group 2, which are less common to be insoluble. So they're insoluble with carbonate. So we're going to add something like sodium carbonate to precipitate out those. Then we're left with our group 1 and ammonia ions. And typically the way that we can differentiate between those ions is by doing a flame test because they glow different colors depending on what the metal is. So this chart right here kind of summarizes all that we first did, or excuse me, all that we just did or just talked about. So the first thing we're going to do is add hydrochloric acid to get our source of chlorines to take out our insoluble chlorides. Then we're going to add hydrosulfuric acid, which is going to remove our acid insoluble sulfides. Then we're going to add sodium hydroxide, which is going to take out our base insoluble sulfides and any hydroxide insoluble compounds. Then we're going to add the carbonate, which is going to precipitate out any of our insoluble carbonates. And then here we can possibly do that flame test to tell the difference. Something else to be aware of is just a qualitative way to distinguish different compounds. Some of our metals are colorful. Transition metals are the most likely to be colorful when they are solid or when they're aqueous. Groups 1 and 2 are typically white. So if you are ever asked, you have a solid that is blue, which of the following is possible? Or you have a solid that's not white, which is fine as possible. Look for the transition metal. Those are the ones that are most commonly going to be colorful. Ones that you're used to seeing, copper is bright blue. Lead is bright yellow. That's an example, like lead iodide or lead chloride. So again, groups 1 and 2 are typically our white typical solids, like what you're used to seeing, like table salt. And then some of our transition metals are brightly colored. Last but not least, make sure you know your solubility rules. Just refresh yourself on those, okay? So basically the thing you've got to remember, group 1, never ever insoluble. Nitrates, never ever insoluble. Ammonia, never ever insoluble. Acetate, never insoluble. So then beyond that, we kind of know, okay, if those are always soluble, then we can kind of usually pick out the ones that are insoluble. Okay, our last type of qualitative analysis that we're going to talk about is chromatography. And this is something some of us, most of us, have probably done, even if you did it as a kid, where you do like a black permanent marker and you put it in alcohol and then it soaks up and then you see all the different colors separate out. That's chromatography. So separating chemical mixtures into its components, so just like any other type of qualitative analysis. In chromatography, we always have 2 parts. We have a stationary phase and a mobile phase. So we have a part that stays still and we have a part that moves. The components are separated by traveling through the stationary phase at different rates. It could be there are different affinities, like one is more attracted to the mobile stage or one is more attracted to the stationary phase, or it could be based on size. And so we're going to look at different types of chromatography. The first is paper chromatography, and this is what, if you've done chromatography, this is probably the type that you have done. So the stationary phase is a solid. It's usually called chromatography paper, which is made out of cellulose. And then there's a mobile phase, which is liquid, most common acetone, alcohol, something like that. And what is going to cause the different components to separate is the polarity. So if the mobile phase is more polar, the things that are more polar are going to travel further. And vice versa. If the mobile phase is less polar, then the things that are less polar are going to travel up further. The example given here in the picture, you might have done it in biology, is separating the different chlorophylls out of a leaf. So you see the different pigments, separated at different rates. Another type of chromatography is called thin layer chromatography. So this time our stationary phase is actually a solid and then the mobile phase is a liquid. But it's going to look very similar in that we're going to see the different separations. The solvent's going to move upward. And this is also based on polarity. So whatever your mobile phase is, the things that are most like it will move the furthest. The things that are the most like your stationary phase, least like your mobile phase, are going to move the least. Another is liquid column chromatography. So that's where we actually pack a column, such as a syringe can be used. You'll see pictures of that in just a second, or even up to these like big glass columns. But we're going to pack it full of a solid, usually silica or alumina. And then our mobile phase is again going to be liquid. And again, it's going to be based on the polarities that they separate at different rates. So in the next slide, what I'm going to show you is pictures when one year, pre-COVID, I took the AP chemistry class to the Museum of Science downtown, and we actually did a chromatography experiment where we separated out pigments. So you notice we have our column chromatography. What they did was they packed it full of sand, and then we had a liquid phase, which I believe was like ethanol, and then we had purple pigment. So it was like purple dye. And what you see as it traveled through the column, the purple pigment, which started here, as it traveled through the column, traveled at different rates. So we see that the red traveled the fastest, then the purplish or the darker. It's really just the combination. It's really the red traveled and then the blue. So you see, as it was, words are hard. As it was expelled from the column, as it dripped through and out of the column, you notice that it was all red, and then it was a little bit of a mixture, which is what gave us the purple, and then it was all blue. So you can see this was first and this was last. So the different pigments traveled through at different rates. The red had the highest affinity for the mobile phase, and so it traveled with it the fastest. Another type of chromatography is size exclusion chromatography. So this looks a little bit like filtration, The stationary phase is a solid. It's usually these like little tiny beads. Mobile phase is again a liquid. And then, of course, the larger molecules are going to travel faster than the smaller molecules because the smaller molecules are going to get stuck, and so it's going to take them longer to travel. Size exclusion, it's not chromatography, but size exclusion is kind of how masks work with the virus right now, right? So it's trapping things in it that are so small they get trapped. So kind of the same idea. Next, we have gas chromatography. So the stationary phase can either be a liquid or a solid. And then, of course, based on the name, the mobile phase is a gas. It's usually something that's inert. It's not going to react with anything like argon or helium. And so this is going to separate things out based on their boiling points. So this is one that uses boiling points to separate the different parts of the mixture. So here's an example AP question on chromatography. We see it's on paper chromatography, and they're looking at dyes. So the student has a sample of 3 different dyes, A, B, and C, and an unknown sample that contains one of the 3. The student prepares the chromatography chambers shown above. They put a drop of each of them at the indicated position, so right here. So first of all, when we're doing chromatography, obviously we need to start everything at the same spot. That's got to be a constant. If we're doing, if we're comparing different materials. So then, this is the other part that's really important. The chromatography paper is polar, and then the solvent or the mobile phase is non-polar. And so then it shows us the results of what happened. So that's important for us to note that the paper itself is a polar material, while the solvent or the mobile phase is non-polar. So A says, which dye is the least polar? Justify your answer in terms of the interaction between the dyes and the solvent, or between the dyes and the paper. So if we look, B traveled the slowest, the least distance. C traveled the furthest, which is the most distance. So the solvent itself is non-polar, so C must be the most non-polar, while B must be the most polar. This makes sense. B was attracted to the polar paper, so it moved very slowly, while C was attracted to the non-polar solvent, so it moved faster with the solvent. So this question said, which of the following is the least polar? And so that would be C. It traveled farthest with non-polar solvent. And then which dye is present in the sample? We're going to compare. Now, something that you have to note here, they both started at the same, but look, the second with the unknown did not allow it to travel as far. So if we look at how far it did travel compared to the other one, it traveled further than B, but less than A, but again, we let the whole front travel less. So if we kind of proportionally brought this down, we would say that this is most likely dye A. All right, guys, that is it. That is all of Unit 6 and all of first semester. Congratulations.